let me begin by giving you just a very short recap of what we did last time. So, so first of all, we had the Dirichlet inner product. And what this was is for functions f and g, we defined their inner product to be given by 1 over 2 pi times the integral of the gradient of f dotted with the gradient of g. And we use this inner product to define a Hilbert space h of d. And this is just the completion of the set of compactly supported C infinity functions in D with respect to this inner product. Okay, so this is the space that we're working with. And the Gaussian free field, H on D, this is given by the sum, as n goes from 1 to infinity, of alpha n phi n, where here the alphas are IID normal 0, 1, and the phis, these are an orthonormal basis of h of d. Okay, and what else did we do? So we also showed that if we have functions f and g, which are in the space h of d, then it's true that, first of all, you can make sense of the Dirichlet inner product of your Gaussian free field with, say, f. And this is going to be a normal random variable with mean 0 and variance given by the norm of f squared. And moreover, we calculated the covariance of these two Gaussian variables that you get when you take the inner product of h with f and h with g. And this is just given by the Dirichlet inner product of f and g. And then the last thing that I want to remind you of is that we also showed that if d is bounded, then the Gaussian free field h takes values in the space h minus epsilon of d almost surely for each epsilon positive. And this is what allowed us to define the L2 inner product. So we can integrate the Gaussian free field against test functions which are sufficiently regular. So these are for functions f, which are in h epsilon of d, whenever epsilon is positive. Okay, so that's pretty much what we did last time. So now what we're going to do today, what we're going to do is we are going to first of all, we're going to derive the covariance function for what you get when you integrate the Gaussian free field against a sufficiently nice test function in the L2 sense. Then we're going to derive the Markov property for the Gaussian free field. We're also going to prove today that it is conformally invariant. And then finally, if there is any remaining time, I'm going to just give you one result regarding the absolute continuity properties of the Gaussian free field. And then next time, so later, the plan is that we're going to look at what's called the circle average process for the Gaussian free field, which is a way of regularizing it so that you get something which is actually a function. And then also we'll look a bit at the theory of what are called local sets of the Gaussian free field. And this is something kind of related to the Markov property for the Gaussian free field, but you don't condition on its values on a deterministic set, but rather a random set. All right, so let's begin with this covariance function. All right, so here's the statement. So let me state this as a proposition, and what it says is that if you have let's say f, which is in h epsilon of d, where epsilon is positive, then it's true that that the L2 inner product of h with f, this is a Gaussian random variable, so it's a Gaussian random variable with mean 0, and its variance, which I'm going to write as sigma sub f squared, is given by what you get when you take your function and you integrate it against the Green's function. So here, this g, this is the Green's function for the Laplacian on d with Dirichlet boundary conditions. So let me just remind you that that the Green's function, this is characterized by two properties, namely number one, its Laplacian, let's say in the first variable, is given by minus 2 pi times the delta function at y. So if I take the Laplacian of the Green's function in its first variable, then I get that, where this is the Dirac mass at y. And number two, g of xy is equal to 0 whenever x or y is in the domain boundary. Okay, so this is just a reminder of what the Green's function for the Laplacian is. And then the second part of the proposition gives you that if you have two functions, f and g, which are in h epsilon of d, then the covariance of the Gaussian free field integrated against f with the Gaussian free field integrated against g, this is just given by the integral of f and g against this Green's function. Okay. And if you remember what we did for the discrete Gaussian free field, you see that this is oh, yep, I forgot a g. I have one g, but I need two of them. There we go. Right, so this is just the kind of natural generalization of the covariance function that we derived for the height field of the discrete Gaussian free field. All right, so let's give the proof of this. So it's pretty simple. So what we're going to do is we're going to write the first n elements in the series expansion for the Gaussian free field. I'm going to call that h sub n. So here, as always, the alpha n's are IID normal 0, 1, and the phi n's, these are an orthonormal basis of h of d. Okay. And now, since this is just a finite sum, just goes up to this capital N here, there's no difficulty in making sense of this as a function. I mean, it is just a function. OK, so what do we have? So if I take h of n, h sub n, and I integrate it against my, my test function, then this is just exactly equal to the integral of hn of x times f of x dx. And now I can write this in kind of what might seem like a little bit of a funny way, but this is the same thing as the integral of hn of x times the Laplacian of the inverse Laplacian of f of x dx, because these two things are just going to cancel. And then I can do an integration by parts and get that this is equal to minus the gradient of hn of x dotted with the gradient of the inverse Laplacian of f of x, like that. And this, this is the same thing as minus 2 pi times the Dirichlet inner product of hn with the inverse Laplacian of f. OK, so just did a little bit of calculus. And if you take a limit of this guy now, as n goes to infinity, then this is going to converge in distribution to a Gaussian random variable, which has mean 0 and variance given by what you would get if you had replaced this hn here with just the Gaussian free field. And so from our formula from earlier, this is just going to be the norm of the inverse Laplacian of f times this factor here, 2 pi squared. OK, so we get that. OK, so we've just gotten that if you integrate the Gaussian free field against a given test function, then it's a Gaussian random variable with mean 0 and this variance here. And what we're going to do now is just do one more calculation, which will convert this formula from the variance here into the one that I wrote over there. So let's just do that. So, so we have 2 pi squared times the norm of the inverse Laplacian of f. And this is the same thing as 2 pi times the integral of the dot product of the gradient of the inverse Laplacian of f times the gradient of the inverse Laplacian of f. And this guy I can integrate by parts again, and I get minus 2 pi times the integral of the inverse Laplacian of f times the Laplacian of the inverse Laplacian of f. And this is the same thing as minus 2 pi. Actually, let me write it a little bit more suggestively. This is the same thing as minus 2 pi times the inverse Laplacian of f times f. But just from the definition of the Green's function, we know that we can represent the inverse Laplacian in terms of the Green's function. And so this is just, in the end, going to give us the integral of f of x gxy f of y dx dy. Okay. OK, so that proves the first part of the proposition. So we've gotten the law of the Gaussian free field integrated against a nice test function. And the way that you identify the covariance function when you integrate the free field against multiple test functions is basically the same thing. So the way that you derive the covariance of the L2 inner product of h with f and h with g, this is completely analogous. So this is derived in a completely analogous fashion. Okay. Now, at this point, let me just mention, one kind of nice exercise that you can try to do if you want to, if you want to understand this better, and that's that you can try to show, using what we've done so far, is you can try to show that if you take the discrete Gaussian free field on, let's say, a lattice approximation of the unit square. So if I just take the unit square and I approximate it with the integer lattice scaled by 1 over n, you can try to show that this converges as n goes to infinity to the Gaussian free field in the continuum, the one that we've just been working with now, also on the unit square. So this is a nice problem to think about because this uses, or at least one way to do this, uses a lot of the different things that we've discussed so far. So you can do this in h minus 3 minus epsilon for any epsilon positive. So with respect to that topology, or you can also just do it in the space of distributions. You can use a weaker topology. All right. So now let's turn to the next topic for today, which is the Markov property. So here's the statement of the result, or this fact, and that's that if we have a bounded domain in the complex plane, and we have a subset of our domain which is open, then if H is a Gaussian free field on D, then we have that this H can be written as the sum of H1 plus H2, where here H1 and H2 are both in H minus epsilon of D, and they're independent. And H1 is going to be harmonic inside of U, and H2 is just a Gaussian free field in U, and just to emphasize, it's 0 outside of U. Okay, so this is the statement of the Markov property for the Gaussian free field. Here's let me just write down a kind of a more informal way of stating this. So kind of more informally, you can say that the conditional law of the Gaussian free field restricted to U given its values off U, so on the complement of U, this is given by the sum of the harmonic extension of the values of H from the complement of u, so from d minus u to u, plus an independent Gaussian free field on u. Okay, so this is kind of a more informal way of stating the Markov property for the Gaussian free field, because you have to be very careful when you make statements like what does it mean to take the harmonic extension of the values of the Gaussian free field, because the Gaussian free field is not a function, it's rather a distribution. Okay, so let's prove this now. Let's prove the Markov property. So here's how it goes. It's going to be just like what we did for the discrete Gaussian free field. So we're going to start off by introducing some spaces. So I'm going to let h harm of u. This is going to be the set of functions in h of d which have 0 Laplacian in u. And I'm going to let h sup of u, this is going to be the set of functions in h of d which are supported in u. And just like in the discrete case, we have the following lemma. And this lemma says that these two spaces together, h harm of u and h sup of u, these together give an orthonormal decomposition of h of d. And this is kind of the main fact that will let us prove the Markov property. Sorry, orthogonal decomposition. Okay, so let's prove this. So let's first prove that these two spaces are actually orthogonal. So let's suppose that that we have f, which is in h harm of u, and g, which is in h sup of u, then their inner product is going to be equal to 0 because if you just write it out and then do an integration by parts, you can put the Laplacian onto f. And this is going to be 0 because f has 0 Laplacian in u, and g is equal to 0 on the complement of u. Okay, so it's pretty easy to see that these two spaces have to be orthogonal. All right, so what I'm going to do now is I'm going to prove that these two spaces actually span h of d, and I'm going to do it in such a way so that I can collect a fact that I'm going to want to use when I finish the proof of the Markov property. Okay, so to show that these spaces span, or these subspaces span all of h of d, let's fix f in h of d, and we want to show that we can represent this as a sum of elements, one in h harm of u and the other one in h sup of u. Okay, so what I'm going to do is I'm going to let f tilde, this is going to be the orthogonal projection of f onto h sup of u. Okay, and then what we want to show is what we need to show here is that if I take f and I subtract from it f tilde, we're going to call this f hat, then what we want to show is that this is actually an h harm of u. Okay, so that's our goal. And what do we know at this point? Well, we know that by orthogonality, the integral of the gradient of f times the gradient of g is going to be equal to 0 whenever g is in, well, g can be in h sup of u. But let's use a very special subset of this. Let's use the compactly supported and C infinity functions inside of h sup of u. Okay, so that has to be true. And what you might like to do at this point is you might like to do an integration by parts to put the Laplacian onto f and then try to argue that because the integral of the Laplacian of f against any C infinity function which is supported in u is equal to 0, that actually f has to be harmonic. But the kind of annoying technicality here is that all that you know about this f hat is that it's in h of d. So you don't in particular know at this point that this function even has a Laplacian. So you have to be a little bit careful here. And so rather than putting the Laplacian onto f hat, what we're going to do is we're going to put the Laplacian onto g. So this is the same thing as saying that the integral of f hat times the Laplacian of g is equal to 0 for all g in all g which are C infinity and supported in u. Okay. And what this tells us is that this f hat, this is actually a harmonic function, or it's harmonic in the distributional sense, in the sense of distributions on u. All right, and now what I'm going to do is I'm going to explain why, if f is harmonic in the distributional sense on u, it's actually C infinity and harmonic on u in the usual sense. So here's the claim that will finish off our proposition, and that's that f hat, this is actually C infinity on u, and it's also harmonic on u in the usual sense. In other words, the Laplacian of f hat at x is equal to 0 for all x in u. Okay, and upon showing this, we'll finish the proof of the proposition. And this has a name. This is what's called elliptic regularity. And if you've taken a graduate level PDE class, then you've probably seen this before. What I'm going to do for you now is I'm not going to give you the full proof of this, but I'm just going to sketch a sequence of steps that if you were to sit quietly by yourself, you would be able to carry out in not too much time. So let me just give you the sketch of the argument. To prove this, so what I'm going to do is I'm going to fix a function which is radially symmetric, compactly supported in C infinity, and it's going to be a bump function. And what I mean by this is that this is a C infinity function. Sorry, let me give it a name. Let me call it phi. And what I mean here is that if you evaluate phi at a given point in z, then this is a function only of the modulus of z. That's what it means for it to be radially symmetric. I'm also assuming that this function is greater than or equal to 0. And then finally, the integral of this function is just going to be equal to 1. Okay, so this is a nice bump function. Okay, and then finally, oops. And then finally, for each positive epsilon, I'm going to let phi sub epsilon be what you get when you just scale this function, scale everything by epsilon. Okay, so this is also a nice bump function. Okay, and then I'm going to let f sub epsilon be what you get when you take f and you convolve it with phi sub epsilon. So to prove this this kind of basic version of elliptic regularity, you just have to follow a sequence of kind of elementary steps. The first one is you can show, and this is just like calculus, that f epsilon, for each epsilon, this is a C infinity function. This is C infinity. Okay? Secondly, if you let u sub epsilon, this is just going to be the set of points in U such that the distance of x to the boundary of U is at least epsilon. Then what you can show is that if x is in U epsilon, then the function which takes you from a given value of delta to f sub delta of x, this function is constant for as long as delta is smaller than epsilon. So for delta to between 0 and epsilon. And let me just, right. Okay, so for all delta small enough, this function is actually going to be constant. And the way that you prove this is that you can just compute the derivative of f delta with respect to delta and show it's equal to 0. Okay, so this step the first step you might see immediately just looking at it. The second one requires just a little bit of thought, and here is one of the places where we use the fact that this f was supposed to be harmonic in the distributional sense. I mean, basically what happens when you differentiate this guy with respect to delta is you'll see that this can be expressed as the integral of f against the Laplacian of something, and therefore, because it's harmonic in the distributional sense, you're actually going to get 0. So this is a really nice, so that's very nice. And then third, you can show that this f delta, this is harmonic in the distributional sense on u epsilon for all delta between 0 and epsilon. And this is again just going to come because we assumed that f was harmonic in the distributional sense. Now, if you have a function which is c infinity, like f delta, c infinity, and it's also harmonic in the distributional sense, then you can conclude that that f delta is actually harmonic in the usual sense in u epsilon for all delta between 0 and epsilon. And once you have that, then you're basically done, because you get that f is harmonic, because you know that f delta is both harmonic in u epsilon, but also doesn't depend on delta. So when you send delta to 0, this just converges to f. I mean, it is just f. So therefore, this function f is just harmonic in u. So yeah, this is a very nice exercise, because this is kind of an elementary way to prove this type of elliptic regularity set, this type of elliptic regularity result in this sense, where you don't really have to use anything, nothing sophisticated at all.
Just a quick question, but your bump function, do you assume that it's supported on a ball?
Yeah, so I should have written that the bump function was supported in the unit disk, just to get the deltas and epsilons correct, right? So let me actually add that just to make this. So I'm going to also assume here that phi is equal to 0 whenever the modulus of z is greater than or equal to 1. All right, and this claim finishes the proof. Because it tells us that f hat, which we showed earlier to be harmonic in the distributional sense on u, up here actually is really a harmonic function in c infinity on u. Okay, and that's it. Now, one thing I want to emphasize, because we're going to use this again in just a moment, and that's that this claim, whose proof we sketched out, this this claim did not require that the function we started off with, f, is in h of d, which we knew to be the case in the context we were using it, but in reality this is actually much stronger. In fact, the same proof is going to work if your f is just a distribution. So it works in a much more general context. Okay, so that's the this is the kind of main lemma that goes into proving the Markov property. And now let's actually prove it. Finish the proof of the Markov property. And this is going to be just like for the discrete Gaussian free field, modulo one technicality. Okay, so let's get started. So let's say we have, we're going to pick two orthonormal bases. So I'm going to let phi n1, this is going to be an orthonormal basis of h harm of u. And I'm going to let phi n2, this is going to be an orthonormal basis of h sup of u. Then the lemma that we just proved, this implies that phi n1 and phi n2 together give a basis of all of h of d. Okay, because these two spaces are orthogonal and together span the entire space. Okay, so what this means is that we can expand our Gaussian free field using this basis. So we can write our h as the sum over alpha n1 times phi n1 plus alpha n2 times phi n2, where here alpha n1 and alpha n2, these are IID normal 0, 1. Okay, and this first part here, I'm going to call this one h1, and the second term I'm going to call h2. Okay, and these are going to be exactly the h1s and h2s in the statement of the Markov property that I just erased. All right, so now it's clear that h2, this is a Gaussian free field on U because it is just given as a random linear combination of an orthonormal basis of h of u. Okay, since this phi n2 here, this is an orthonormal basis of h of u, because that's the same thing as, or can be identified with, h sup of u. Okay, and that tells us that since this is a Gaussian free field, h2 has to be in h minus epsilon of u, and therefore it is also in h minus epsilon of d. And because we can write h1 as h minus h2, this is also going to be in h minus epsilon of d, because it's given by a linear combination of two elements which are in h minus epsilon of d. Okay, and so to finish, what we have to do is we have to show that this h1 here actually is a harmonic function inside of u. And sorry, let me also add here that it's clearly true that h1 and h2 are independent, because the coefficients in their series expansions are independent. So these are independent. Okay, and now let's just finish by showing that h1 is harmonic. And to do that, I'm going to let h1 superscript n just be the truncation of the series expansion for h1 up to n. Okay. Then this function clearly is harmonic because it's now just a finite linear combination of harmonic functions. Okay. So then h1n, this is harmonic in U. And this implies that if I have any test function which is compactly supported in C infinity in U, then by harmonicity, the integral of the Laplacian of h1n against f of x, this is going to be equal to 0. And if you do an integration by parts, this is the same thing as the integral of h1 of n against the Laplacian of f. And if you take a limit as n goes to infinity, this is just going to converge to the L2 inner product of h1 and the Laplacian of f. Okay. And since all of these things are equal to 0, it follows that this is equal to 0 too, and so h1 is harmonic in the distributional sense on U, so it's also harmonic on U. Okay, and that finishes the Markov property. So here we're using kind of the stronger version of the claim that we used in the last lemma. Okay. Yep.
So here you had like the convergence in distribution or in h minus epsilon of this harmonic function. So is it also like convergence in local in compact sets? Like because we can now see just U, so the
Right.
harmonic, so we can see it as a function.
Right.
How does it converge as a function to the other?
So all that we're using here is that in the limit, we're not trying to show that. So you can show that the approximations here, these do actually converge uniformly on U. That's something that you could show, but that's not what we're showing here. We're just showing here. We're just using here the fact that the approximations converge in this weaker sense.
No, I was asking what you could show actually.
Oh yeah, so you can also show directly. Another way to approach this is that you can just show that this guy is not going to be blowing up when n goes to infinity, because you can calculate like a variance of this at a given point, and then using regularity stuff for harmonic functions, you can kind of argue that it's not going to be blowing up, and therefore, this is going to be bounded, sequence of bounded, So yeah, there's another way to do this too. You don't have to go this way. All right, so in the last 10 minutes, let's do the conformal invariance of the Gaussian free field. All right, so this is conformal invariance of the Gaussian free field. And what the result says is that, let's suppose that D1 and D2 in C, these are bounded domains. And we have a map, phi, which goes from D1 to D2. And this is a conformal transformation. And whenever I say this, what I mean is that phi is conformal, and it's also a bijection. Okay, then the statement is that if H is a Gaussian free field on D2, then H composed with phi is a Gaussian free field on D1. Okay. So you have your two domains, D1, your map which goes from D1 to D2. And if we start off with a Gaussian free field over here, then it's going to become a Gaussian free field when you precompose with phi on the left-hand side. And since we're getting a bit short on time, I'm just going to kind of explain the main lemma, why the Gaussian free field should be conformally invariant, and then we'll stop there. So the main thing that gives you the conformal invariance of the Gaussian free field, main input, is the conformal invariance of the Dirichlet inner product. And what this says is that if you have the same setup as in the previous proposition, so the same setup as above, and we have two functions, f and g, which are in H of D2, then it's true that f composed with phi and g composed with phi are both in H of D1, and the inner product of f with phi and g with precomposed by phi is just equal to the original inner product of f and g. Okay, so this is the conformal invariance of the Dirichlet inner product. This might seem a little bit surprising if you haven't seen this before, because there's no correction here like a Jacobian that comes from this change of variables. So it might look like it's a little bit fishy, but if you just look at this by inspection, you can see that, well, first of all, it's obvious that it's just obviously true if your phi is a rotation so that's very obvious, and slightly less obvious, but still obvious, is that this is true also if phi is given by just a rescaling. Okay, so these two versions, kind of weaker statements, you can check just by using the change of variables formula. So it doesn't use anything special yet about this map being conformal. And I don't want to do the full proof of this because it's a little bit computational. But let me just indicate how you do it, and then you can check it on your own if you want to. So for general phi, you just do a calculation where you apply the change of variables formula. And you apply the change of variables formula when you're calculating this first inner product here. So you start to calculate this one. And And when you do this, you're going to see a lot of derivatives. When you start calculating this, you're going to see a lot of derivatives involving this conformal map phi here. And to handle these derivatives and get enough cancellation so that this actually pops out, what you have to do is use the Cauchy-Riemann equations. And then most of the terms that you get will just cancel. Okay, and if you just carry out this calculation, you'll see that this has to be the case. But this is too tedious to try to explain. Do this all on the board. All right, now let me just finish the explaining why the Gaussian free field is conformally invariant. Using this lemma. So let me just indicate the idea here, and then we'll stop. So essentially the reason that it follows is that if you have h given by the sum of alpha n times phi n, where phi n is an orthonormal basis of h of d2, and the alpha n's are IID normal 0, 1, then the previous lemma, this lemma we just did, this implies that phi n composed with phi, this is an orthonormal basis of h of d1, because the Dirichlet inner product is preserved under conformal maps. And so h tilde, which is given by h composed with phi, this can be expressed as, in the usual way for a Gaussian free field on D1. Okay, and that's how you show the Gaussian free field is conformally invariant. And so what we've done so far today is we've shown that the Gaussian free field is both conformally invariant, and it satisfies a Markov property, which is very similar to the Markov property that Vincent showed earlier, is satisfied by and characterizes SLE. And what we'll start to see a little bit later is that, in fact, what this suggests, which is that the Gaussian free field and SLE are very closely connected, turns out to be the case, and they are in many different ways. And I think I'll stop there. Does anybody have any quick questions? Okay, so